So I wanted to remind you that when we had a frictionless track, this is the LOL chart that we made, and this was the resulting equation that we wrote. Was it the elastic energy at position A was equal to the gravitational energy at position B? But now, in this scenario, we are now including the track in the system because we're accounting for the friction that would be there. And so I'm going to put track inside the system there, like so. And so now the question is, how does that affect my LOL chart? Well, would it affect position A? Well, no, not really, because position A is at the beginning. It hasn't had a chance to rub up against anything. It's at rest, compressed. So therefore, position A stays the same. What about position B? Well, position B, it is the wheels have moved. It's spun on the axle, thermal energy loss in the axle itself, but also thermal energy loss between the wheels and the track. And so therefore, there should be thermal energy accounted for. And if you think about doing this experiment, like if I did this on like a really thick carpeted ramp versus a really smooth ramp, it's not going to go as high if it's a carpeted ramp because there's going to be a lot of thermal energy loss. So to account for that, I just need to take 1 bar of energy and move it over here. So now the question is, how do I write my equation? Well, again, the energy at A has to be equal to the energy at B. And so my equation should be, okay, well, what's my energy at A? Well, my energy at A is EL at A. Okay, well, that's got to be equal to, and notice, if you ever get confused about this, just think about simple addition. 3 is equal to 2 plus 1. So then just instead of using numbers, substitute in the type of energies. So 3, EEL, is equal to 2, which is EG at B, plus 1, which is ETH at B. So now the equation is a little bit more complicated because I got the thermal energy in there, but this now would account for friction. And so when I account for friction, this is the equation that I now have.